Assalamualaikum warahmatullahi wabarakatuh and a very good morning to Madam Suhaida and my fellow friends. I am Ayu Najah binti Rashid and with me is my partner Shamimi Amani binti Syari. Today, we will be presenting our chosen question which is question 6. I am 100% sure you guys might not remember what question 6 is all about, so please stay with us until the very end of this video. The contents of this video are shown on the screen right now, which are introduction, solving the problem, the potential application, and lastly, the conclusion. So, without further ado, let's start with the introduction. Semiconductors are materials whose electrical conductivity lies between conductors and insulators. Unlike conductors, which allow electricity to flow easily, and insulators, which strongly resist current flow, semiconductor exhibit controlled electrical conduction. This property makes semiconductor suitable for use in many electronic devices such as diodes, transistor, and integrated circuit, or also known as IC. Silicon is one of the most common used semiconductor materials. Electrical conduction in silicon occurs due to the movement of two types of charge carriers, namely electrons and holes. There are two main types of silicon, which are intrinsic silicon and n-type silicon. In intrinsic silicon, the material is pure, so the number of electrons equal to the number of holes, and both contribute to electrical conduction. However, the carrier concentration is low, resulting in low electrical conductivity. On the other hand, n-type silicon is formed by doping the silicon with donor impurities. This process increases the number of free electrons, making electrons the majority carriers. As a result, n-type silicon has a much higher conductivity compared to intrinsic silicon. Therefore, the main difference between intrinsic silicon and n-type silicon lies in their charge carrier concentration, which directly affects their electrical conductivity. Question 6 asks us to compare the conductivity values between intrinsic silicon and n-type silicon. The question also gives us the values of intrinsic carrier concentration, electron mobility, hole mobility, as well as electronic charge. Now, let us proceed to solve this problem. I will explain how to get the conductivity value for intrinsic silicon. Meanwhile, my partner will explain the conductivity value for the n-type silicon. To calculate the conductivity value for intrinsic silicon, we need to list out the given data first, and the given data in the question includes the intrinsic carrier concentration, which found to be 1.5 times 10 to the power of 10 per cubic centimeter. The values of electron and hole mobility are given by 1300 cm square per watt second and 500 cm square per watt second respectively. Last but not least, 1.6 times 10 to the power of negative 19 coulomb is the given value for electronic charge. To get the conductivity value for intrinsic silicon, the intrinsic conductivity sigma I is given by electronic charge Q times intrinsic carrier concentration Ni multiplied by the sum of the electron mobility Me and the hole mobility Mh. Substitute the value given and the conductivity value for intrinsic silicon is found to be 4.32 times 10 to the power of negative 6 per ohm centimeter. The value is quite low due to the small value of intrinsic carrier concentration.
Next, let's find the conductivity value for n-type silicon given that electron mobility equals to 1300 cm² per volt second. Electronic charge equals to 1.6 times 10 power of negative 19 coulomb, and assuming donor concentration equals to 10 power of 15 per cubic centimeter. To find the conductivity value for n-type silicon, we can use the formula, which is conductivity equals to electronic charge times donor concentration times electron mobility. And with the given value, we substitute into the formula and then we get 0.208 per Siemens centimeter. Intrinsic semiconductors such as pure silicon play an important role in modern electronic and opto devices mainly as the fundamental material before doping is introduced. Firstly, intrinsic silicon is used as the base or substrate material in transistor fabrication. Although transistors require dope P-type and N-type regions to operate, they are initially fabricated on intrinsic silicon wafers because of their high purity and controlled electrical properties. This ensures reliable performance in microprocessors and logic circuits. Secondly, intrinsic semiconductors are important in diodes and high-frequency electronic devices. The low natural carrier concentrations allow better control of current flow, making them suitable for rectifiers and fast-switching applications. Next, intrinsic silicon is widely used in photodetectors. When light strikes the intrinsic semiconductor, electron-hole pairs are generated, producing an electrical signal. This principle is applied in light sensors, cameras, and optical communication systems. Lastly, intrinsic semiconductor layers are used in solar cells, particularly in PIN structures. The intrinsic layer improves light absorption and enhances charge carrier collection, leading to higher efficiency. N-type silicons play a critical role in modern electronics due to its high electron concentration and superior electrical conductivity. One of the most important applications of N-type silicon is in power electronics and high voltage devices such as power MOSFETs, IGBTs, and diodes. N-type silicon exhibit low on resistance and high switching efficiency. These properties make it ideal for applications in electric vehicles, power supplies, and industrial automation systems where efficiency and reliability are essential. Next, N-type silicon is fundamental to CMOS logic and advanced integrated circuits. In CMOS technology, N-type and P-type regions work together to form transistor, precisely control N-type doping, improve drive current, increases operating speed, and reduces power consumption. This is especially important in high-performance devices such as CPUs, GPUs, and mobile processors. In addition, N-type silicon is increasingly used in solar cells and photovoltaic systems. Compared to conventional P-type silicon, N-type wafers are less affected by light-induced degradation. As a result, they offer better long-term stability, high efficiency, and increased energy yield in solar power applications. Finally, N-type silicon is widely used in sensors, detectors, and MEMS devices including image sensors, photodetectors, and Hall effect sensors. Its low noise and stable electrical properties enhance sensitivity, measurement accuracy, making it highly suitable for optical and sensing technologies.
To solve a conductivity problem, we first read the question carefully to identify what is being asked, then list all of the given data such as carrier concentration, mobility, and charge. Next, we choose the right formula for intrinsic and N-type silicon since both types use different formulas. After that, substitute the values into the formula and please make sure the units are consistent. After calculating the conductivity for both types, we compare the result to determine which one is higher, and finally, state the conclusion clearly, highlighting the type with the highest conductivity.
In conclusion, understanding conductivity in intrinsic and N-type semiconductors is fundamental in solid-state physics. It explains how doping increases charge carrier concentration and electrical conductivity. This knowledge allows engineers to control material properties and design efficient electronic devices such as transistors, integrated circuits, and solar cells. Without this concept, modern electronics and energy technologies would not be possible. This concludes our presentation. Thank you for your attention.